Okay, so picture this. You're bundled up inside while a winter storm is raging outside. Winds are howling, snow is piling up. It feels like the whole world is just caught in this like whirlwind of icy fury. Sounds intense, right?
Apparently.
Well, that's the reality of a bomb cyclone. These aren't your average winter storms. These are meteorological monsters that just deepen with astonishing speed. And they leave behind a trail of destruction, but also awe. I mean, one resident of St. John's, Newfoundland, after a bomb cyclone in 2017, they described it perfectly. They said, I've lived here my whole life and I've never seen anything like it. The snow was piled up so high we couldn't even open our front door.
Wow.
So that's the kind of power we're talking about here.
Yeah.
What makes a bomb cyclone tick? How does a storm go from like a quiet murmur to a full-blown blizzard practically overnight? Today we're diving deep into the science behind these rapid intensifications. We've got some fascinating sources, scientific articles, meteorological definitions, even a study about how these storms get portrayed in the media.
It's really captivating to see how bomb cyclones showcase the raw power of nature, driven by a delicate balance of atmospheric forces. And while the term bomb cyclone might sound a bit dramatic, it really does accurately reflect how explosive these events can be.
Okay, so let's break down this bomb analogy a little bit. I mean, we're not talking about like literal explosions, are we?
No, not in the traditional sense, no. The bomb part of that term refers to this rapid and dramatic drop in atmospheric pressure, which is a hallmark of these cyclones. Officially, for a storm to be classified as a bomb cyclone, its central pressure has to plummet by at least 24 millibars within a 24-hour period.
24 millibars in 24 hours, that sounds like a pretty steep drop.
It is, and to make things a bit more interesting, this criterion isn't like a one-size-fits-all rule. It actually gets adjusted based on latitude.
Yeah.
Because the Earth's rotation, the Coriolis effect, that plays a huge role in how these storms develop.
Okay, so a storm that's brewing near the poles needs a bigger pressure drop to be considered a bomb cyclone, compared to one that's forming closer to the equator.
Exactly. The Coriolis effect is weakest at the equator, and it's strongest at the poles. Imagine walking in a straight line across the spinning merry-go-round. The closer you are to the center, the easier it is to walk straight. But the further out you go, the more you're going to get deflected by that spinning motion. Same principle applies to storms. At higher latitudes, you have a stronger Coriolis effect, so you need a greater pressure drop just to generate the same spinning motion.
That's a really great way to visualize it. So latitude adds another layer of complexity to the whole bomb cyclone equation. But what are like the fundamental ingredients that set the stage for these intense weather events in the first place?
Think of it like a recipe for some extreme weather. First, you need a really strong temperature gradient, a clash between a mass of cold, dry air and a mass of warm, moist air. Often oceans come into play here, providing a source of both moisture and warmth. That's why bomb cyclones are especially frequent in regions like the North Atlantic and the North Pacific, where cold continental air can collide with that warm ocean air.
Okay, so we've got our clashing air masses, our temperature battleground, if you will. What else do we need to kickstart this atmospheric drama?
You need upper-level atmospheric support, a powerful jet stream, that river of fast-moving air high in the atmosphere, that can enhance the rising motion of air, which further fuels that pressure drop we were talking about at the surface.
So it's like the jet stream is fanning the flames of the storm's development.
Precisely. And of course you need ample moisture. This moisture often originates from the ocean. It feeds the storm's clouds and precipitation, and as that moisture condenses, it releases latent heat, which further warms the air and intensifies the storm's upward motion.
Okay, so we have our ingredients, clashing temperatures, a jet stream that's stirring the pot, and a healthy dose of moisture. But how do these factors actually translate into that rapid intensification that defines a bomb cyclone? That's where the science gets really interesting, right?
Absolutely. The key is understanding how these ingredients interact to create a feedback loop. That accelerates the storm's development. Let's start with this concept of thermal wind.
Thermal wind. Is that related to how temperature differences can actually create wind?
Exactly. Imagine two columns of air side by side, one warm and one cold. The warmer air is less dense, so it expands upwards, creating a pressure difference between those two columns. This pressure difference forces air to move from high pressure to low pressure, which is what we experience as wind. And because this pressure difference increases with height, the winds at higher altitudes actually become much stronger.
Okay. I'm starting to see how that temperature difference translates into wind. But how does it lead to that spinning motion that we associate with cyclones?
That's where this concept of baroclinic instability comes into play. This instability arises when you have a strong temperature gradient and wind shear. meaning the wind changes direction and speed with height. The atmosphere doesn't like being tilted like that.
It's like a stack of books that's leaning precariously, just waiting to topple over.
That's a great analogy. Just like that stack of books, the atmosphere wants to rebalance itself. It does this by forming waves and eddies, which eventually develop into those rotating cyclones.
So the atmosphere tries to right itself. And in the process, we get these swirling storms. It's amazing how nature seeks balance even in the middle of chaos.
It is. And this interplay of forces, this dance between temperature gradients and wind shear, and the Earth's rotation, that's what fuels this rapid intensification of a bomb cyclone. Now scientists have developed mathematical models, like the ED model, to simulate and predict this growth rate.
So it's not just about the ingredients themselves, it's also about the rate at which they combine and react with each other. That determines the intensity of a bomb cyclone.
Precisely. Now, there are two other important concepts that play a role in the intensification process: vorticity and divergence.
Vorticity and divergence. Can you explain what those are and how they contribute to this meteorological mayhem?
Vorticity is essentially a measure of the atmosphere's spin. Think of it like a spinning top. Divergence, on the other hand, refers to the spreading out of air. In a bomb cyclone, you have this convergence of air at the surface. It feeds into the low pressure center. This convergence forces air upwards, creating an area of low pressure at higher levels. This upward motion is crucial because
as that air rises, it cools, leading to condensation and
you got it, latent heat release. Remember all that moisture we were talking about?
Right.
When that water vapor condenses into liquid water or freezes into ice, it releases heat into the surrounding atmosphere. This heat warms the air, making it less dense and further enhancing that upward motion. It's a positive feedback loop that contributes to the storm's rapid intensification.
So we've got this swirling mass of air powered by temperature differences, wind shear, and even the heat that gets released from condensation. It's a chain reaction of sorts, each step amplifying the next.
Exactly. Now we've talked about how meteorologists approach bomb cyclones, but physicists also bring their own unique perspective to understanding these events.
Oh, okay. So how do physicists view these meteorological marvels?
Physicists delve into the fundamental laws that govern fluid motion, energy conversion, and phase changes. They use complex equations like the Navier-Stokes equations.
Navier-Stokes equations. That sounds a bit intimidating.
Don't worry, we won't get bogged down in the mathematical details. Essentially, these equations describe how fluids like air and water respond to forces. By applying those equations to the atmosphere, physicists can model and analyze the intricate motions within a bomb cyclone.
So it's like using the same principles that govern the flow of water in a river to understand the flow of air in a storm.
Precisely. And the beauty of physics is that it helps connect these seemingly disparate phenomena. Like, for example, the Coriolis effect that influences the rotation of a bomb cyclone. Also, it affects large-scale weather patterns and ocean currents. It's all interconnected.
It's amazing how these deep dives always reveal those unexpected connections. Now, I know we've talked about meteorology and physics, but what about the math behind these storms? How do scientists actually quantify this meteorological mayhem?
That's a great question. And that will lead us into the world of numerical weather prediction. We'll delve into that in the next part of our deep dive.
All right, I am ready to tackle the math behind these meteorological monsters. We'll be back soon to explore how scientists use equations and models to predict and understand these powerful forces of nature. All right, so we're back and ready to dive into the world of numerical weather prediction. I have to admit, the idea of using math to predict something as chaotic as the weather, it's kind of mind-blowing.
It is quite remarkable. But at its core, numerical weather prediction relies on those fundamental laws of physics, the ones that govern every aspect of our world. We left off talking about those equations that describe the motion of fluids, like the Navier-Stokes equations. These equations are incredibly complex. They involve multiple variables and some really intricate relationships. Solving them directly for the entire atmosphere, that would be a computational nightmare.
So how do scientists actually use these equations to make weather predictions then?
That's where those numerical weather prediction models come into play. They essentially take these super complex equations and make them solvable by using clever approximations and computational techniques. One really common simplification is called the quasi-geostrophic approximation, or QG for short.
Quasi-geostrophic approximation. That's a mouthful. What exactly does it simplify?
Essentially, it focuses on the large-scale dynamics of the atmosphere, particularly the balance between the wind, the pressure gradient force, and the Coriolis effect. Remember, the Coriolis effect is that apparent force caused by the Earth's rotation. It makes objects moving across the Earth's surface deflect to the right in the northern hemisphere and to the left in the southern hemisphere.
Right, it's like that merry-go-round analogy we were talking about earlier. The further out you are on the merry-go-round, the stronger that deflecting force becomes.
Exactly. And for large-scale flows like those involved in bomb cyclones, this balance between the wind and the Coriolis force, it's crucial. So the QG approximation simplifies things by focusing on this balance, allowing us to analyze those flows much easier.
Okay, so we're simplifying those equations by focusing on the most relevant forces. But how do we go from these simplified equations to an actual weather forecast?
That's where computational techniques like finite difference methods come in. Imagine dividing the atmosphere into a grid, like a giant checkerboard.
So each square on this checkerboard would represent a specific location in the atmosphere.
Precisely. At each grid point, we can assign values for variables, like temperature, pressure, wind speed, and direction. Then the model uses those grid point values and the equations to calculate how those variables will change over time, essentially simulating how the atmosphere will evolve and consequently the bomb cyclone.
So it's like taking a snapshot of the atmosphere at one point in time, and then using math to predict how that snapshot will evolve.
You got it. And the finer that grid is, meaning the smaller those squares on our checkerboard are, the more detail the model can capture, leading to more accurate forecasts. Of course, finer grids also require more computing power.
So it's a trade-off between detail and efficiency.
Exactly. Choosing the right grid resolution really depends on your specific forecast needs. For bomb cyclones, which evolve so quickly, a finer grid is generally preferable to capture those rapid changes in pressure and wind.
Makes sense. So we've got our equations, our approximations, and our computational grid. What else goes into building a reliable weather forecast?
Another crucial aspect is data assimilation. This involves blending observations from a bunch of different sources like weather balloons, satellites, surface stations, into the model.
So it's like taking the model's initial guess and then refining it with real-world data.
Precisely. These observations provide a reality check, helping to nudge the model in the right direction and improve its accuracy. And this process is ongoing. As new observations come in, they're continually integrated into the model. It creates this dynamic feedback loop between prediction and reality.
It's like the model is constantly learning and adapting, just like we do. Now, earlier you mentioned a concept called potential vorticity, or PV. How does that fit into this whole forecasting puzzle?
Potential vorticity is a fundamental concept in meteorology, and it's especially relevant to understanding these bomb cyclones. In simple terms, PV is a measure of the atmosphere's spin, but it takes into account both the rotation of the air itself and the Earth's rotation.
So it's like a measure of how much swirling energy is packed into a particular air mass.
That's a great way to think about it. What makes PV so valuable is that it's conserved under certain atmospheric conditions.
Conserved, meaning it doesn't just like disappear or change randomly.
Exactly. This conservation principle allows scientists to track the movement and evolution of air masses, including the ones involved in bomb cyclones. By following the PV, it's like having a tracer die that lets you see how a fluid is moving and mixing.
So by analyzing PV, meteorologists can identify areas where bomb cyclones are likely to form and intensify.
Precisely. And there's this technique called PV inversion, where if you know the distribution of PV, you can actually work backwards to figure out the wind and temperature fields associated with it. It's a super powerful tool for understanding the structure and dynamics of these storms.
It's like knowing the dance moves and figuring out what music goes with them. So PV is like a key piece of the puzzle when it comes to predicting and understanding these bomb cyclones. Now, I know we've talked a lot about the science and the math, but what about the real-world impacts of these storms? They're not just numbers on a screen. They're forces of nature that can have a pretty profound effect on people and ecosystems.
You're absolutely right. And that's something we should definitely delve into further. Let's shift our focus from the theoretical to the practical and explore some of the consequences of these powerful storms.
Okay, so we've spent some time unraveling the scientific and mathematical threads of bomb cyclones, but now I think it's time to ground ourselves back in reality. These storms aren't just these abstract concepts. They have real-world impacts, and sometimes those impacts are devastating.
You're absolutely right. Bomb cyclones can bring this whole host of hazards with them. Hurricane force winds, torrential rainfall, coastal flooding blizzard conditions, even high surf and rip currents. Their impacts can range from disrupting transportation and causing power outages to some severe damage to infrastructure and, tragically, even loss of life.
It's a sobering reminder that these are forces of nature that demand our respect. Can you give us some specific examples of the kind of damage these storms can inflict?
Sure. Back in 2021, a record-breaking bomb cyclone formed in the Northeast Pacific. This storm slammed into the western coast of North America. It brought hurricane-force winds, heavy rainfall, and massive flooding. To regions of the United States and Canada, the damage was extensive. It exceeded $400 million. And sadly, several lives were lost.
Yeah, that's a really stark reminder of the power these storms possess. And I imagine the impacts go beyond just that immediate damage and those economic costs.
You're right. Bomb cyclones can also have some really long-lasting effects on ecosystems. For instance, one research paper highlighted how these storms can impact marine life. Fishermen reported numerous dead fish washing ashore after a bomb cyclone. This was likely due to those rapid changes in water temperature and pressure caused by the storm.
It's heartbreaking to think about those cascading effects that these storms can have on entire ecosystems. As our climate continues to change, are we likely to see more frequent or more intense bomb cyclones?
That's the million-dollar question that scientists are actively researching. There's no definitive answer yet. But some studies are suggesting that a warming climate could actually create conditions that are more favorable for bomb cyclone development, like warmer ocean temperatures. Those could provide more fuel in the form of moisture and latent heat. And changes in atmospheric circulation patterns could also enhance the temperature gradients and wind shear, the same ingredients that drive these storms in the first place.
It's a good reminder that understanding these storms isn't just an academic exercise. It's crucial for preparing for and mitigating the potential impacts of a changing climate.
Exactly. Before we wrap up our deep dive, there's one more fascinating aspect of bomb cyclones I wanted to touch on. It's their interaction with the upper atmosphere, specifically the tropopause.
The tropopause. That's the boundary between the troposphere, where most of our weather happens, and the stratosphere above it, right? What role does it play in the whole bomb cyclone story?
The tropopause is a lot more dynamic than people might think. It can undulate, ripple, even fold in response to atmospheric disturbances. And these undulations, particularly the formation of troughs or dips in the tropopause, are often linked to the development and intensification of bomb cyclones.
So it's like the tropopause is creating a pathway for the storm to intensify.
Exactly. A dip in the tropopause that's located above a developing bomb cyclone. That often coincides with an area of low pressure and strong winds aloft. This can actually enhance the upward motion of air within the cyclone, further fueling its development.
It's like someone opening a window at the top of a chimney, allowing all that smoke to escape more easily.
That's a great analogy. There's also another interesting phenomenon that can occur. It's this downward intrusion of stratospheric air into the troposphere.
Stratospheric air mixing with the air we breathe. What happens then?
Stratospheric air is very dry and ozone-rich. This intrusion can actually alter the temperature and moisture profiles within the storm, sometimes even suppressing precipitation in certain areas. It's a reminder that what's happening way up high in the atmosphere can have a huge impact on the storm's evolution down below.
It really highlights the interconnectedness of our atmosphere. Speaking of connections, didn't you mention that potential vorticity, or PV, plays a role in the whole tropopause story as well?
Absolutely. Those tropopause undulations are often associated with the strong gradients of PV. When stratospheric air intrudes into the troposphere, it often brings with it these high values of PV, which can then interact with the PV associated with the developing cyclone. It's like two spinning tops colliding, creating this complex dance of swirling energy.
Wow, I'm starting to see how all these pieces fit together. The initial ingredients, the rapid pressure drop, the role of vorticity and divergence, and now this interplay between the storm and the upper atmosphere. It's like a whole symphony of atmospheric forces, each one playing its part in this meteorological drama.
And that's the beauty of studying bomb cyclones. They challenge our understanding of the atmosphere, and they really push the boundaries of our scientific and mathematical models. Every new bomb cyclone event gives us more valuable data and insights that refine our knowledge and help us better predict and prepare for these powerful storms.
Well, I think we've done a pretty thorough deep dive into the world of bomb cyclones today. We've explored their formation, intensification, impacts, even their interaction with the upper atmosphere.
I agree. We've covered a lot of ground. And I hope our listeners are walking away with a deeper appreciation for the complexity and power of these meteorological marvels.
As our planet continues to change, understanding these storms, and really all aspects of our dynamic atmosphere, is going to become even more crucial. So keep those questions coming, stay curious, and we'll see you next time on The Deep Dive.